Welcome to qnawire.
This is problem number 58 of the Stewart Calculus 8th edition, section 2.8. Part A. If g of x equals x to the 2/3 power, show that g prime of 0 does not exist. All right, let's use the definition here in green to solve g prime of 0. So a will be 0 in this case. The limit as x approaches 0 of the function g of x, which is x to the 2/3 power, minus the function evaluated at 0, 0 to the 2/3, divided by x minus a, which is 0. Here we're just left with x to the 2/3 over x, limit as x approaches 0. So x to the 2/3 divided by x will be 1 over x to the 1/3. And as x approaches 0, this limit does not exist, since we cannot divide by 0. So in part A, g prime of 0 does not exist. Part B, if a is not 0, find g prime of a. So we're using the same definition. G prime of a equals the limit as x approaches a, except a is not 0, of the function g of x, which is x to the 2/3, minus a to the 2/3, so the function evaluated at a, divided by x minus a. To simplify our answer a little quicker, we're going to write the numerator and the denominator in terms of x to the 1/3 and x to the 2 and a to the 1/3. So the first term, x to the 2/3, can be thought of x to the 1/3 as squared, and then a to the 2/3 can be thought of as a to the 1/3 squared, and then x minus a can be instead x to the 1/3 cubed minus a to the 1/3 cubed. And the reason we want to do this is because we want to convert the difference of squares in the numerator and the difference of cubes in the denominator and factor them the way that we see here. These are known formulas for the difference of cubes and difference of squares, and that'll allow us to simplify a lot faster. So limit as x approaches a. We're using these formulas where capital A is equal to x to the 1/3, and capital B is a to the 1/3. So our difference of squares is going to be, in the numerator, it's going to be a x to the 1/3 minus b, which is a to the 1/3, x, or a plus b, and the denominator is a little longer, but we should have a minus b, or x to the 1/3 minus a to the 1/3, multiplied by a squared, or x to the 2/3, plus a times b, which is x to the 1/3 times a to the 1/3, plus b squared, or a to the 2/3. Okay, and here we see how this works out for us, because we can remove or cancel these two terms because they're equal. And our next step will be to evaluate the limit as x approaches a. So every x becomes an a. Here we have a to the 1/3 plus a to the 1/3. That's 2a to the 1/3. And then the denominator, we have a to the 2/3 plus a to the 1/3 times a to the 1/3. That's a to the 2/3 as well. And then we have another a to the 2/3. So that's 3a to the 2/3. Great. Now we can simplify a little more, and we see that our derivative should definitely be 2 over 3a to the 1/3. And this is our final answer for part B, g prime of a. 2 over 3 times a to the 1/3 in the denominator. Part C, show that y equals x to the 2/3 has a vertical tangent at 0, 0. So essentially, we're going to use this result, this derivative, um, because what this derivative means is the slope of this function. And a vertical tangent line has a very characteristic slope. So as a approaches 0, just like we showed in part A, but more correctly in part B, it's going to be this limit as x approaches 0 of the function that was given to us, g of x minus g of 0 over x minus 0. And it's going to be this function 2 over 3a to the 1/3 at a is 0. And if a is 0, the denominator is 0. And so this limit as a approaches 0, or as x approaches 0, goes towards infinity. So this is what we expect for a vertical tangent, is that the slope approaches an infinite value. The slope gets more and more and more and more positive, and then it gets absolutely vertical. And that's what we expect to see at the origin, is that the slope reaches an infinite undefined number. Part D, illustrate part C by graphing y equals x to the 2/3. So here we have a graph of that function, x to the 2/3, and we see that there is this corner, this cusp here at x equals 0, and we see that the slopes of the tangent lines get more and more negative to the left of 0, and they're more and more positive as we get closer to 0 from the right, meaning that there is a vertical tangent line here at the origin. So we have confirmed part C by graphing the function y equals 2/3, and that means that everything that we have shown is consistent